to finish off looking at power, I've got a second example where we've got a few more variations in there. So here we've got a car again, mass 1,000 kilograms, travelling on a horizontal road with a constant speed of 5 meters per second. That's badly written there. The non-gravitational resistance forces are 400 newtons. So again, separating gravity out here. Initially, it wants us to calculate the power produced by the engine. So part A, fairly straightforward. We need to set up our diagram. We've got our flat surface. There's our car. We've got resistances of 400 newtons. We have a constant speed of 5 meters per second. So we have no acceleration. Obviously, we've got a force which is coming from the engine. And again, because we've got no acceleration, our forces are balanced. So we know that F must equal 400 newtons. So it's got to equal those resistive forces. Now from there, we can jump straight to our power is equal to force times velocity, which is just 400 times by 5, which gives us 2,000 watts. Okay, nice and straightforward for part A there. So that's the power produced by the car. Now, the road becomes inclined at an angle of, great typing skills there again, 10 degrees, and the power is increased to 20 kilowatts. Find the initial acceleration of the car. Now that word initial is quite important there, because as the car accelerates, the velocity will change, and so the force produced by the engine will change. So we're just looking at that initial situation. So again, let's get our diagram drawn. So here's our road now at an angle of 10 degrees. I'm not going to put the car right at the bottom, but it's a model. We know what we mean. We still have 400 newtons going down there. That doesn't mention any change to the resistive forces. It will normally say the resistance forces stay the same. We still have a force being produced by the engine. We still have a velocity of 5 meters per second, but now we are going to have an acceleration as well of 8 meters per second squared, and that's what we're trying to find out. Last thing, if we refer back to the question, it said right at the top we had a mass of 1,000. So on our diagram, don't forget that we need our 1,000 G acting down. Okay, now from here, I'm going to start by resolving parallel to the slope, up the slope there. What we have there is our force minus 400 minus 1,000 G sine 10 equals MA. Okay, now we're fine with most of that. We just need to work out this force. So that's going to come from power is equal to force times velocity. We know our power is 20,000 watts, 20 kilowatts. We know our initial velocity is 5. So by dividing, we get our force is equal to 4,000 newtons. Okay, we're now going to take this value and our mass from before. Oops, I missed a naught out up there. That should say 1,000, not 100. We're going to take our mass and our force that we've just worked out and plug them into here to give us 4,000 minus 400 minus 1,000 G sine 10 is equal to 1,000 times A. Okay, now if you plug that straight into your calculator, you should come out with 1898.2479 keeps going is equal to 1000 A. So our acceleration is equal to 1.898, which will neaten up to three significant figures to 1.90 meters per second squared. All done there. And it's just working out that force from the power there and then plugging it all in and working it all through. So now have a look at the questions in the book that go along with this. I'll do one more example during this week of an exam question where this is used.